I'm most excited that you could have come to attend this, in my opinion, very exciting symposium. And my sincere gratitude to speakers, the people who are presenting posters, and the panelists, and also you all attendees. The two key individuals who have made this symposium possible, my former professor, Professor Liang Chua of UC Berkeley, my PhD thesis advisor, who back in 1971 published a seminal paper, which I will show you briefly. This is the last page of his paper. Memristor, the missing circuit element. So mathematically, conceptually, he defined the constitutive relationship between flux linkage and the charge, and then labeled it as memristor. This is a missing circuit element that was published in the IEEE Transactions on Circuit Theory, September 1971. And there he said, although no physical memristor has yet been discovered in the form of a physical device without internal power supply, just as a passive element, the circuit theoretic and quasi-static electromagnetics analysis presented in this paper make plausible the notion that a memristor device with a monotonically increasing phi flux linkage Q charge curve could be invented, if not discovered accidentally. I know Liang as my thesis advisor, just a brilliant person. I had all the benefit of being advisee of Liang Chua. And my thesis involved the extension of a memristor concept on memristive devices and systems. That was a part of my thesis, chapter 2. And then in 1976, we published a paper in the Proceedings of the IEEE on memristive devices and systems. And I remember, I told Liang last night, in fact, Liang, do you remember when I was a graduate student, I asked you this question. As a student, I said, Professor, will I be able to find a job if I work on this topic? And he said, do not worry, if you do, whatever you do, if you do well, you will find the job, he said. I never forget that comment. And then May this year, Dr. Sen Williams of Hewlett-Packard and his team members published this exciting paper in Nature, the memristor missing circuit element found. It's really great invention by Dr. Sen Williams' team. And I owe a great deal to these two individuals who made this symposium possible today. I will leave this one on to continue my remarks. As you know, Richard Feynman, former professor at Caltech, said there's plenty of room on the bottom in terms of a small scale world, scale size world. And I think he was right. Stan found this memristor in the bottom of the world in nanoscale, right? And the other people that I like to thank is Dr. Pinaki Mazumder, who will speak later on. He was, I met him at Illinois when I was a faculty member. Then he became professor at University of Michigan, Ann Arbor. He still is. At the same time, he is program director at National Science Foundation. So when we approached him for this symposium, he was very enthusiastic and played a key role in sponsoring this symposium. And then also thanks to Hewlett-Packard for giving additional support to make this symposium possible. Of course, my alma mater, UC Berkeley, has helped tremendously. Denise Simard, who is sitting out there, She really dedicated enormous effort in organizing this symposium. But more importantly, strong support came from current chair of ECS, Professor Stuart Russell, whom I will introduce later on. And then also I had a great benefit of getting help from UC Merced. Since I'm Chancellor, I was able to get some help without paying them. But Kimberly Preciado, my special event coordinator, she set up all the website, did the electronic registration, and all the arrangements. And then another person, Marisa Dalla Davis, she will also make sure that we have a record of all the proceedings and help me file a report to National Science Foundation. Semiconductor Industry Association and the SRC, the College of Engineering Dean's Office of UC Berkeley, and Dr. Paul Wright of CITRES, acting director, also gave a tremendous help to make this event possible. So my sincere thanks, and again, we have an exciting program today. Stay tuned. Without further remarks, I'd like to invite Professor Stuart Russell to come and make his remarks. Stuart, would you please?
Okay, so my remarks will be very short. I just wanted to welcome everyone here on behalf of UC Berkeley and the Electrical Engineering and Computer Science Department. I wanted to thank Steve Kang for making this happen. He's certainly the only chancellor who answers his email. I never had that experience at Berkeley, that's for sure. And of course, Liang for making this possible. So Liang, as you may know, joined Berkeley in 1970. And this paper was published in 1971, so I like to think that something in the air at Berkeley had an effect on Liang and made him think big and bold. So I think this symposium is really a celebration not of a highly engineered system or an extremely complicated theorem, but of just a pure idea. The paper is really a pure idea paper, and I think it's wonderful that that idea has turned out to have value after all. And as you know, Steve himself was a little uncertain about whether it was going to turn out to be a truly successful idea that it has been. So I'd like to encourage everyone either to have those ideas or to encourage the people who work for you to have those ideas, not be afraid to publish them, and not insist that the idea be turned into a product before it's allowed to see the light of day. Thank you very much.
Before you go down, I have something for you. So, as a small token of appreciation, I prepared a little paperweight here. Oh. So, thank you very much.
Thank you very much, Steve.
Thank you. So we will move on to now technical topics. So first speaker is Professor Liang Chua. Let me introduce him very, very briefly. But I know he originated from Mapua Institute of Technology, MIT of Philippines. And then from there he went to MIT. Actually, his wife, Diana, I don't know whether Diana is sitting right there. She's also MIT graduate. She's chemical engineer, I know. And then from there, Liang went to University of Illinois, Urbana-Champaign for his PhD, where I had the pleasure of being a faculty member. And after graduation, he went to Purdue to teach at Purdue and was already a very established professor. And Professor Ernest Koo, where is Ernie? Ernie is a distinguished ECS professor, and at that time, big giant in circuit theory. So Ernie, Charlie Dussault, Rolf Dissart, they were wonderful people, invited Liang to join the faculty at UC Berkeley, and the rest is the history. What impresses me as a graduate student, Liang, not only he was brilliant, he didn't fully rest on his brilliance. He worked so hard. I always tell my own students, my advisor even didn't take lunch because he thought it was a waste of time. And then as a graduate student, I remember receiving phone call from Liang 2 o'clock in the morning. We had a weekly report, and if he has question, he will call you even 2 o'clock in the morning. That's how he achieved so much. I have a great respect for Liang. I'm so excited for this Memristor development. And let's hear Liang's story, right? Okay, thank you, Liang.
Put it somewhere here. Okay. Good morning. Thank you for coming to participate in this symposium. I was asked by Professor Kang to give a sort of a tutorial on Memristor. So it'll be a fairly simple elementary talk, just to tell. So the question is, what is a memristor? And in order to answer what is a memristor, actually we should ask the question of what is a resistor, what is a capacitor, what is an inductor. And if you look at any standard textbook, the answer, of course, is what we all learned from high school physics, as well as what we taught our students today. This is the definition, okay? And let us examine this definition and see whether that is correct or appropriate. And so let's just look at a capacitor. The usual definition of standard is I is C dV dt. And now if this were correct, then we could, for example, vary the capacitor plates, and let's say make a time varying that would vary according to the sine function, like so. And if we pick that definition that we all learned and we taught to our students even today, you would put I of t is C of t dV dt, and of course you calculate and you put it in the lab and look at the oscilloscope. You want to see whether you have the right answer. So there's this obvious generalization. The generalization of I, C, dV to give the correct current, in the sense that if you measure, look at the oscilloscope, you get the right answer. And surprisingly, the answer is no. And in fact, if you look at this definition, the classical definition, you see it's a relationship between current and the derivative of the voltage. And so it involves two variables, and this is very important. We're always going to see two variables relating each other. The classical definition of a capacitor is that it relates between current and dV dt. And it turned out to give it the wrong answer. But however, if you integrate both sides with respect to time, then the left side becomes charged, and the right side becomes the voltage, which of course is the same equation. And that's only because it's linear. When it's linear, it's the same. It will turn out that if it is not linear, if it's non-linear, or if it's time varying, you see that in fact it is not the same. And it will turn out that it is this formula, this second definition, that gives you the right answer. And of course the reason, if you now put the time varying function here, you would get Q of t is C of t Vt. And so when you differentiate to get a current, both sides, you would get C dV dt, the usual term, plus an extra term because now C of t is varied with time. So this is the missing term that makes the formulation wrong. And so the moral here is that it was just an accident that we have used IC dV dt, and that's not the correct definition to give you the right answer. There is an analogy to that, by the way. You know, think of a rocket you're launching with a force versus velocity. And we all learned F equal ma or m dV dt from high school physics. But if you were to use this formula, you would get the wrong answer because the mass, as the fuel get burned, the mass decreases. So the mass, it varies with time. And if you would just put this function of time in this F equal ma, you would get the wrong answer. NASA would never be able to launch a spacecraft if they would use this formula. And of course, the reason is you should use the correct formula, which is the relation between the momentum and the velocity, which means that you have to integrate both sides variable, and you take the p, the integral of that, and the velocity on the right side, the integral of acceleration is velocity. And then if you would then put the time-varying mass, and you would get this extra term that was missing. So the important thing is in trying to identify model of a new device or new system, it's important to find out what is the relevant variables. So at least for the capacitor, we now know that the relevant variable is between charge and voltage, and not between current and dV/dt. And that is true for whether you have a straight line or a relationship such as that. So therefore, a capacitor really is no more than a device that constrains between the charge and the voltage. And any such device is called a capacitor. And of course, if this is a straight line, then you have Q is equal to CV. Okay. So this really is the concept that led to this definition of what are the basic circuit elements, in the sense that it will give you the correct answer when you make measurement. And so we start with the four fundamental variables: the voltage, current. We already knew that in capacitor you actually need the charge, which we just defined to be the integral of the current, and then likewise flux, we just define integral of the voltage. Now some people get confused when they start to look for flux and charge in the Memristor device, and if you get confused, just forget about the name. Just use that as a symbol, and because it's not it's only in certain special cases that it's relevant to think of charge and flux. For circuit analysis, it is just the integral of current and voltage, and we just have a symbol, and we just give it a name, the charge and flux. Okay, so by the same token, now you can ask. There are four variables, and you can now define a device that makes a constraint between voltage and current. Any such device is now called a resistor, and likewise, any device that would constrain a relationship between the flux and the current would be called an inductor, mainly because that gives you the right answer. That's the only reason for modeling, okay? So if we sort of organize this definition of mine in the form of a diagram, so this is the voltage, the current, and this is the flux and the charge, and these two, of course, are already related by definition. Likewise, the voltage and the flux are related by definition. And and with this diagram, we see that, of course, that anything that relates between voltage and current is what we call resistor. Anything relates between voltage and charge is what we call capacitor. Likewise, current and flux is the inductor. And if this is the correct, if this indeed gives you the right answer, then you would obviously would ask, what about this missing link? Okay, and so this is obviously if this theory is going to be correct, there's got to be something there that will complete it, and I therefore just define it and introduce that symbol, and I call it a memristor, contraction for memory resistor, and we will see why it is a memory resistor in a short while. But before I do that, I sort of want to sort of give you a bit of a analogy. In fact, this way of defining circuit element is actually dates back, I mean, to Aristotle. If you look at Aristotle's Physica, he says that all matters consist of four elements: earth, water, air, and fire. And he went further to say that the way you distinguish them is that there are four variables: how moist it is, how dry it is, how cold it is, how hot it is. And so Aristotle actually postulates that fire is the relationship between hotness and dryness. And air, this is straight from Aristotle. I just redraw them here, okay? And of course, now you can see the striking resemblance. It's always the relations between relevant variables, okay? So this is, in fact, nothing new. It's back Aristotle's time, okay? All right, so now let's get serious on memristor. Now that we have defined memristor is any device that that constraint make a relation between the flux and the charge, which we say call any smooth curve. Okay, so flux is a function of q, or you can say q as a function of phi, either way. And so you can now find the voltage, because if you differentiate both sides, V is d phi dt, or d phi df dq, dq dt, and dq dt, of course, is just a current. So although this is the correct definition, but if you want to see the meaning, what it does is that it's actually a relation between voltage and current, and like a resistor, it's linear. Okay, and so whatever that quantity is has the unit of ohm. So it's really Ohm's law, except that this is the resistance, except that the resistance changes with the operating point. So you have, so depending on where you operate, you would have different resistances, and I call them memristor, memory resistance. So let's just look at a special case for the current interest is in non-volatile memory. So let's just suppose that we have only two, for simplicity, two slopes, and I plot this in the flux versus charge plane, so that the slope is the resistance here, and so when the slope is small here, you say this is 1, so it's 1 ohm, and when you operate in this region, you have 10 ohms. Okay, so you can think of this as two states. You either have 1 ohm or 10 ohm. This will be the binary state that will be used for the memory. Now, of course, we all know that if with an electronic circuit, if you such as a tunnel diode, if you want to bias at a point, you will put in a battery, and you need a battery. Okay, and so you have this different operating point. This is the flip-flop in this case. But if you put a plug, which means you take away the short disk, the load line, of course, would go there, and you're back to 0, and you lost all memory. You lost all information. That's why you need to keep refreshing in DRAM, and it's volatile. Now, how is it that in Memristor you can put a plug and you still remember? And it's very simple, because remember, let's reply this in a Q phi plane. Phi is flux, okay? And now suppose I apply a voltage pulse, a short pulse, okay, of duration delta and high E, and when the pulse go back to 0, it's just like you put a plug. There's no more power, okay? But if I can operate at any point I want, for example, if I just starting from 0 initial condition, here at T0, I say at 0, and I integrate this to get my flux, okay? And when this go back, you put a plug, the voltage go back to 0, the current go to 0, but the flux stays there. So it means that you put a plug then, and the point stays there, and that's where the memory comes in, And the reason is that I have proved some years ago that you can never use voltage or current or charge or flux as memory, in the sense that if you put a plug, it disappears, it leaks through even the capacitor when you connect with something else. Okay, now some people had a difficulty feeling how you can retain memory, and so I want to give you a real analogy here that you can understand. Think of this mechanical dashpad. In the linear case, it's just friction. So the force of friction is just the friction force. Let's say this thing is sliding through a friction wall with velocity. We all know that that's a friction. But what if you make a modification of this dashpad or this in the following sense? Suppose you imagine that this is a bag of thick rubber, and you have a hole here that's of course a rubber, so it's elastic, and now you have a friction pipe. I mean a metal, for example, that is tapered. So now you can see that the formula is still correct. F is still resistance, the friction times the velocity, but the friction would be different depending on the position of how much how thick it is, and so this would be the exact analog of a memristor, and where x now is the displacement from the origin, and so in fact the way so this is no longer a mechanical memristor. In fact, you should define it now not between f and v, but between the velocity, the integral of f and the integral of v, which is momentum and displacement. And if you do that, so that this mechanical memristor is defined exactly now. It's a relationship between momentum and displacement, so that when you differentiate both sides, you would get dp dt back to force, and this is back to the velocity, and this is your memristance, and this is therefore exactly this formula. And so we actually have a perfect example of a memristor that you can understand, and the memory depends on where you are, how much friction you have. So if you want to have a binary case, you just make your memristor with two different diameters. So on the left of that you have high friction, in the left you have low friction. So you have a binary memristor. And in fact, with this interpretation, you can see that you can actually, so this is the memristance curve, okay? Here you have only two slopes, but you can see now that you can just taper this any way you want it and to produce any memristive curve that you want. And for example, you can have a Coca-Cola there, and depending on the diameter, this will be the perfect memristance, okay? Now you can understand why it is where the memory is, okay? All right, now, so the memristor is, to summarize, is defined by the voltage is the memristance times the current. Let me see if I get this a little bit better. Okay, now you have seen, of course, this mechanical memristor, but the question is it possible? Is it possible to build a passive solid-state memristor? Because if you can, then you have a non-volatile memory. And I asked this question in 1971, and I showed that I proved a theorem which says that it is possible if the characteristic curve is monotone increasing. That's the theorem. So now there was no reason why it doesn't exist. But nobody, of course, has found that until Sen Williams and his wonderful lab sort of came up with this brilliant invention called the memristor. And now a lot of people start to say that, oh, we found that also 2 years ago, 5 years ago, I even have a paper there, and it behaved the same thing. But they're missing the point is that the invention here is to identify what is the mechanism. Nobody really knows how it works. And I hope that Stan will also explain how he came about. So this is the device that the SP invented, and he will hear a lot more about that. And what they found, what Stan found and his group found, is that the voltage is a memristance times Q and times I, and that they actually have the exact formula. That's this one, and these are all constants, which is not important. What's important is divided by the length of this. This is made of titanium dioxide, by the way, and these are just two platinum electrodes. So it's very, very simple. And this curve, by the way, if you, I'm reproducing what they had, is a charge versus flux. It's monotone increasing as predicted. And it was truly a tribute that they were able to even have a formula. So this is truly an ideal memristor. And also it's that simple. They also can make it apparently very small, possibly within up to about 2 nanometers, as I was told. And so that would be really fantastic if you can get it that small. And Stein would probably say, I'm sure would say a lot more. And this stuff, this titanium dioxide, by the way, is wonderful. It's stuff that you all know. You know, you go to go to Greece, and this great white pen. This is where the white pen came from. The pigment is exactly the titanium dioxide. Except that in making this work, Stan will show you later, is that you would extract some oxygen so that there's some vacancy, and so that makes that an ion. And what's remarkable is that if you now put a battery here, and so you started with a bit of a oxygen vacancy, they become positive ions. So with applied voltage, it will be a suck up there, and that's the mechanism, and it's almost like a champagne, you know. It just bubbles, just move up, and that in fact is I believe exactly the mechanism, and Stan will explain more. So that's the SP memristor, you know. But I would tell you that there are many more other devices that people now found behave the same way, and I'm going to talk a bit more about that. But it's not that there are other devices. Is that identifying what makes it work, what's the mechanism? Because if you don't, you would never be able to design a device, make it commercial, and make it practical. So the question, how do you know, by the way, your device is a memristor? In fact, if people would only know this, they would have found it years ago. And if you know it's a memristor, for example, to find out is because V is just Ohm's law, or I is conductance and V, which means that if you plug in any periodic signal, when V is 0, I is gonna be 0, or vice versa. Okay, and so you have a signature. In fact, you put in any signal in there, they all go through the axis at the same time. They have the same 0 crossing, and the translating this into the IV plane simply means that you will have a loop. Just make it nice, but it could be any loop that and that it has to always go through the origin. It's got to always. I call this pinch hysteresis loop. That is the single most important signature of a memory. If you have a device and you found that you got a pinch hysteresis loop, you will see it is either a memristor or is a memristive device that I'm going to talk next, which is what Professor Kang just told you early on that he did as part of his PhD research. Okay, now the fact that it goes through the origin and that goes through a serial crossing means actually that there is no phase shift, of course. That there is it's impossible to store energy. There's no energy storage, so it's purely dissipative. And so if you have a light bulb, for example, we all know that if you have a charged initially capacitor and you close the thing, you're going to get some flickering of light. Likewise with inductor, but not so with a memristor. Nothing will happen. It just has no energy storage. It's a purely dissipative device. And another signature of a memristor is you can prove quite easily that putting any periodic signal, you will always get a pinch loop, but the pinch loop is going to change shape and gets actually shrink as you increase the frequency, and that's another signature. So there are all kinds of things to identify whether you're looking at a memristive device or not. Now it turned out that memristor actually is something that exists in nature, only embedded until you look for it. And I want to show you one interesting. This is Josephson, Brian Josephson, and he got, of course, his Nobel Prize for the paper called the Josephson Junction. And in this paper, Josephson actually showed that this is part of the Josephson paper, that there are 4 terms here. One of them is, and he modeled them as a capacitor, and the second term is a resistor, and then a third term is an inductor. But there is another term here that he didn't know what it is. But fortunately, this is a very small quantity, so that in most practical application, it can be neglected. But if you translate Josephson's model, Josephson's model is only this part, and throw in his unknown effect, and that is quantum mechanical effect from particle pair, from quasi-particle pair in quantum interference current. And if you actually now look at that equation, you will see that it's nothing more than a memristor. It's an exact memristor. So it's already, it exists in part of natural system as well. Okay, now let me move on to again back to memristor, and from memristor I want to move on to show you that this is the work, the second paper that Professor Kang has just mentioned. And so it turned out that we can easily generalize it to a much broader class. So if you start from this equation, V equal to mq dq dt equal to I, and simply just change the variable, Q, there's no reason why it should be a single variable, and there's no reason why it should be charged. So why not just make this Q to be any number of variable you want, called a state variable, provided that you, for each state variable you introduce, you relate it to itself with respect to the current. So in other words, this is a generalization of that. In this trivial spatial case, you recover the charge here. And this is what we call a memristive system. And of course, it has all the same property. Everything is the same. And that's why my symbol for the memristive system is this figure 8 with a pinch hysteresis loop. And it turns out that there are many such devices that exist in nature, and of course it includes the Memristor now as a special case. And I want to show you at least a few examples. Let's go back to this light bulb. A light bulb that, most people thought, because the light bulb is just nothing interesting, it's just a resistor, but that's not quite true, because when you apply the voltage, the resistance heats up, and when it heats up, it changes the resistance, and then the temperature has to interact with the environment. So you can actually write an exact equation that says that the voltage is a constant times the temperature times the current. That's, of course, is now the memristance. Now this is not charge, it's temperature, but that's part of our definition. And the temperature obeys the heat balance equation, and this is the heat balance equation. So it's a state variable depends on itself plus the current here. It's a perfect example of a memristive device, and this is known way back in the 30s. In fact, there was a book published by in applied physics, a paper in 1952, and sure enough, they plotted, and because they never realized that the significance. You can see this pinch loop. These are a different frequency. They all have this pinch loop that go through the origin, and so that's a perfect example of a memristive device. And then I tried to trace way back, and I found a paper recently, and this is paper published 1936. This is in German, okay, but this is about this again a lamp, and when you apply the sinusoidal voltage, you heat up the thing, and so the temperature changes and it actually flickers. And in this paper, he actually refers to another paper by Corbino, who was 1910, that also observed similar effects. And in this paper, in fact, they had plotted a curve there. This is the excitation signal sine wave, and they have this variation which can be translated indirect into a change in resistance, if you wish. So one can say that the memristive device is nothing new at all. It's almost 100 years old if you trace back to Corbino, and of course they would not say that, and I mean they don't know what they're looking at, but they just realize that the resistance changes with temperature. It doesn't stay constant. But more recently, let's look at our neuron. In another fundamental paper, if this is the axon of a neuron, so if you look at the axon and try to model that, this was done by Husky and Huxley that got the Nobel Prize in 1961. It's called the well-known Husky and Huxley model that is still widely used today. It's in fact one of the fundamental papers ever, 1952. But in that paper, Husky and Huxley showed that the model of the axon net membrane consists, in addition to the usual capacitor and a resistor, but he said that there is he called it a time-varying conductor conductance or resistor, and a potassium conductance and sodium conductance. But unlike the time-varying capacitor that I show you, where you actually can specify how it varies with time, in his case, Husky and Huxley in this paper showed that the potassium conductance, the current, this is Ohm's law again, current is a constant times the voltage, but that conductance is not a constant, it varies with time, and Husky and Huxley said it obeys a form, this G depends on a state variable n, that's not important for today, but that n is a differential equation. So if you ignore the details here, it's just function of n times the voltage. It's a perfect example of a memristive device, okay? And as for the sodium, this is the potassium. In the sodium conductance, Husky and Huxley showed that the current is a conductance times the voltage, Ohm's law again, but it depends, the conductor is not constant, it depends on two state variables, M and H, which is unimportant for today, except that M and H obeys two differential equations each. And so these are the two differential equations where you have two state variables. Another perfect example of a memristive device. So indeed, in fact, memristive device is everywhere, you know. And not only that, but people who studied this paper begin to realize that when you look at low frequencies, for example, the potassium channel behaves like an inductance, and so there were all kinds of controversy after this Nobel Prize paper. He said, so where is the inductance in nerve? There's absolutely no inductance you can think. And the reason is, of course, there is no inductance. It's just they didn't realize that it's a memristive system. And so, in fact, one of the famous papers by Maros even published, say, anomalous. They call it anomalous because they can't explain it. How come you can have inductance? But if they knew that this was a memristive device, and everything would be completely clear that it's there. Okay. And now I want to show you that after the famous HP paper came out, I look back at the literature, the nano literature over the last 20 years, and I showed that there are many, many papers that people published that are memristive devices, or maybe even memristor, and they just didn't realize it. And I want to show you, this is, it dates back further, but I start with the year 2000, and you can see that this is the pinch hysteresis loop, okay? And so they're very fond of publishing VI curve and with a pinch loop, but they just call it hysteresis. They don't know what it is. Here's this earliest that 1976, and I jumped to 2000. Okay, and then I want to show you one example for each year, just to show there are many. I just pick one per year. This is 2001. Okay, and you can see it's a pinch hysteresis loop. 2002. The famous paper by Professor Lieber, who's one of the really outstanding researchers from Harvard University. It's a pinch hysteresis loop. He didn't know, of course, that it's a memristive. 2003, another paper. You got a pinch hysteresis loop. And there are many. I'm just showing you one, just to show you how there are so many, okay? 2004, you have a pinch hysteresis loop. 2005. And as we get more towards the future, there are more and more. 2006, 2007, and 2008. And there are many more. Just to show you that there are tons of them. And of course, none of them realize that they are all memristive devices, maybe not memristor. But some of them could be very close to a memristor. In fact, I've shown already that the Lieber device is almost a memristor. Okay, so in other words, the fingerprint of a memristive system is just like a memristor. Is that the voltage versus current loci will be always a pinch hysteresis loop. That is the signature, and you have seen many of them now. But the question is, how do you know that they are indeed? If you see a pinch loop, we know that if it's memristive, it is going to be pinched. But how do you know if it's pinched is memristive? Well, the answer, it turned out, is in a theorem that I now want to state with you. I call it fundamental memristive system theorem. It says that every two-terminal device which exhibits a pinch hysteresis loop when driven by a DC analog sinusoidal signal is a memristive system, in the sense that we can actually produce an equation for you. The equation may be very messy, but there is an equation that will do it. And the proof of that this year is given in Chancellor Sung-Mo Kang's PhD thesis. You know, he has actually a formula, a sort of shotgun formula. It's impractical. You say that it's very messy, but there is a formula, but that shows that it is memristive. And then you will then go and look more carefully, and then you will try to massage it and come up with simpler formula. So the moral here is that anytime you see a pinch hysteresis loop, you have a memristive system. And by virtue of this fundamental theorem of Chancellor Kang here, okay, that's a proof. So we have a if and only if thing. Okay, now let me move on. So this memristive stuff is great, and of course that is hopefully it is quite possible that a lot of companies are going to be interested, because this is quite a powerful thing. Just imagine you don't have to boot up your computer in the morning, and you can pull the plug, or you go for the coffee, or go for take a 2-week vacation, and you leave your you flow chart there, and just pull a plug. You come back, it's there. You know, you don't read. But the question, what's next? Well, what's next? Of course, hopefully the company is going to start to get their acts together and produce products. But from my perspective, what's next is to look at it more carefully, and then you suddenly, of course, you realize the memristors are not lossless. You know, it cannot store energy. As non-volatile memory, memristors do not consume power when it's idle, when you put a plug, but it does dissipate a little heat when you got to read and write on it. So the next goal that we want to do is to ask the question, what's next? Can we invent a lossless non-volatile memory where you truly, you know, don't even dissipate any heat? And I just found one last week. This two, in fact, you know. I call this a memory capacitor. I haven't found a name yet because if I call it memductor, it just doesn't sound good, okay? So it's memory capacitor is a device that is described by a curve in the sigma versus flux. So sigma is not, it's just you integrate the charge. I don't have a name for that, okay? You just integrate charge, and that is sigma. And if you have such a curve, sigma is some function phi, you can take differentiate both sides. You have d sigma dt is df of phi dt, and but it's df d phi dt. But the f d phi is just because this is charge, this is voltage, so these are the unit of capacitance. So you actually have a charge as it's a capacitance where the capacitance depends on the flux. This device, I can prove, is lossless. In fact, if you make this piecewise linear, you see it's just two capacitors. So you can intuitively see it's lossless, and this would be the ideal one is totally lost, and it is non-volatile. That would be the next goal for the device people here. And now, so the fingerprint of a memory capacitor that I just introduced is again that if you plot in the charge versus flux plane, not in the voltage current plane. If you go to voltage current plane, you won't see it. It'll be something else. But if you go plot between the charge and flux plane, charge as a function of time and flux, it will go through same zero crossing again, and it means that it will have a pinch loop again, but not in the voltage and current, but in the charge and flux plane. And just to show you that it is lossless, I picked this two-state memory capacitor, and I inject this signal in there. That's the voltage, and I will, if you calculate, you see that's the current. So if we multiply the two, then now the voltage go to positive and negative, but the current remains positive. So that power is go up, down, become negative, and at half a cycle it sucks in, it takes in power, but it returns the other part. So that's why it's lossless. Okay, and so that would be the next thing. Hopefully that would be invented someday. And if you have this device, you repeat this experiment. You put in initial flux, put no power, turn the switch. You're gonna glow just like a capacitor. And of course, whenever you have a capacitor, so the theorem is that the memory capacitor is a lossless element, unlike the memory resistor. And of course, as soon as you know you can make a memory capacitor, you can make a memory inductor just by duality. You have a memory inductor, which is just a device that obeys the relationship between the integral of flux, whatever, I don't have a name for that, call that rho, and versus charge. And that would give you a behavior just look like an inductor, except that inductance depends on its charge. So whichever element device will be invented first, I don't know, but it is entirely reasonable that it can be invented. So the memory inductor is also a lossless element. Okay, and I got 5 minutes, so I just want to quickly go back to some of the questions people had asked me over the years. You know, so Ohm's law, of course, started this all, and the Memristor is nothing but just Ohm's law, except that these are changes. So I was asked in just a recent lecture in Munich. I just gave a big lecture, and they called it the Ohm lecture, by the way, because Ohm started at the university in New Munich. So they said Ohm's law was discovered in 1827. Why did it have to wait for 144 years to invent the memristor. And so my answer actually is that that's 144 is nothing. I said, go back to Aristotle. And so I said, I said, how many of you remember Aristotle's law of motion? Nobody raised a hand. I said, well, Aristotle's motion says F equal mv. And the reason they don't remember it is because it's wrong, okay? But it was wrong for 2,000 years. Until Newton comes around, that is the law of motion, okay? And Newton comes around and says, well, you have the wrong choice of variable. So Newton says it's F is equal to ma. If you now take Newton's law and go to Mars and with a high-speed thing, or the velocity of light, we all know, of course, that the relativity tells us the mass it would change and with velocity. And this would be, so if you use a simple-minded way and say, okay, Newton is right, so why don't we just put in this mass as a function of velocity in this place, and that will be Newton's second law, no big deal. But then you look at this formula, you see that it involves the force, acceleration, and velocity. It has three variables. Something is not right. You should not have to involve three variables. And so if you integrate, in fact, this formula, and if you go through the algebra, it will turn out that it is a perfect differential. So that when you integrate, finally you get an equation that relates only the momentum and the velocity. So it actually relates only between momentum and velocity, and of course the momentum, the derivative is the force. And that is the correct formula, of course. And so let me summarize these three formulas now. Aristotle's law says F is equal to mv, and he was wrong because he picked the wrong variable F. Newton's law says that F is equal to ma, and he was wrong in both counts. He's wrong in A, and he's wrong in F. Einstein's law says P is equal to F of V, velocity. So at least Aristotle was right. They got the second variable right. Okay. And if you let, of course, velocity slow, this go to zero, then you recover Newton's law. So this is the same scenario why, when it's linear, or you get misled into thinking you have I, C, D, V, D, T is exactly the same scenario. So the correct law of motion actually is this Newton at low velocity. This is just a straight line, but the correct is Einstein's law with relativity in, and this is the analog. This is the correct definition, and actually translating into my talk today, Einstein's law of motion is nothing more than a nonlinear inductor with that characteristic. Okay, and so with this, I end with one more sentence. I was asked often also after this memristive thing, say people say, why did it take so long for the memristive theory to be validated? And I actually have two quotes that I normally show. And the first quote is by Max Planck, whom all of you know. And Max Planck say, new scientific ideas do not succeed by converting contemporary scientists, but rather by their opponents dying off. So somehow I have outlived them, I guess. And then I have a second slide, which says, this is by famous biologist, and you may not know because he's a biologist, but very famous, Haldane. He says that theories have 4 stages of acceptance. This is worthless nonsense. That's the first comment. Then the second stage say, this is interesting, but perverse. The third one say, this is true, but quite unimportant. And we are now in the 4th stage, I hope. And the 4th stage say, end of my talk.
Okay, so Liang gets one of this one also.
Oh, thank you. Thank you very much.
So maybe we can remove this the overhead projector now. Yes. Somebody, yes. Thank you. Thank you, Leon, again, for very exciting. He's the same. I was a graduate student here between 72 and 75. The enthusiasm is exactly the same. He's a very dynamic speaker. So next two talks will be given by Dr. Sen Williams. First talk is Finding the Missing Memristor. Second talk was one of his colleagues at HP, but he got sick and couldn't be here. So second talk is material implication using memristor and alternative form of Boolean logic. So let me briefly introduce Stan. He doesn't need much introduction, but he's a Berkeley graduate, PhD in chemistry. And then he was a famous professor at UCLA, and then decided to come to HP. Currently, he is a senior fellow of HP, one of the highest honor given to technical staff, and director of a laboratory as well. But his current focus is on central nervous system for the Earth. And he has received many honors, but let me highlight just a couple. He was the first to receive twice, to be named to the Scientific American 50 Top Technology Leaders. So first in 2002, now 2005, and then I'm sure that he will receive another recognition pretty soon. The patent collection by his achievement has been named by Small Times magazine as the world's top technology intellectual property portfolio. MIT's Technology Review placed one of his patents among the top 5 that will transform the business and technology. And recently, his invention has been named by Time magazine as one of the top 50. They put top 13, ranked 13, including all the popular things. And PC magazine put his invention as number 1 in the world. So with that introduction, Stan, the podium is yours.
Thank you very much. So am I on here? And okay. Okay. Well, sorry about that. I thought I had everything all queued up, and so we should come up here any second now. I'd like to thank Steve for all of the tremendous work that he did in putting this workshop together. To think about the Chancellor of a university campus putting so much effort into, well, this thing was working. We had it completely checked out. It was working. Yep, that's absolutely right. So Steve put a tremendous amount of effort into putting this workshop together, and for that, I'm very, very thankful. And of course, I'm also very thankful to Liang, not only for a fantastic introduction to the topic of memristors, but also a challenge to us all for coming up with some new inventions. You can absolutely believe that I'm going to be thinking about memory capacitors and memory inductors very seriously right away. So what I would like to do is I'd like to talk to you about how we essentially found the missing memristor. It was in many ways very accidental. It was not in the quote from the original paper that Steve showed earlier, the prediction was that it would either be found by accident or or it would be invented intentionally. Well, in fact, it was found by accident. And also, as Liang showed, it had been found many, many times, but it hadn't been recognized in many cases because it was in disguise. So this is actually a research effort that's been going on at Hewlett-Packard Labs for nearly 10 years. And the total number of people who have worked on this within our laboratory is about 100 people. So this has not been a trivial effort by any means. And besides the people working in Hewlett-Packard, we've had fantastic collaborations at multiple universities as well as national laboratories, and even some support from government funding agencies as well as HP. So this was not just somebody coming along and stumbling across something and saying aha, and also it wasn't a reading the paper and just figuring it out. This was if you really think about it, it might be close to 500 researcher years of effort that went in to actually making this connection. It seems crazy, in retrospect, but this is what it takes. This is what science really takes. So it turns out to be all related to the nanoscale, and I'll show you why. Liang has already sort of given the overview for that. But I have been working in this sort of area that you might call nanotechnology for some time. And the dilemma has been for quite a while that we claim that the nanoscale is different, but then we go about trying to build the things that we recognize today using nanoscale components. And I think that I finally learned that this is crazy. That if we're really going to say that the nanoscale is important, we should be looking for new things, or at least expressions of old things that we weren't able to express before. And so that's really the primary lesson that we've learned from this. In this presentation, I'm going to essentially introduce to you how we got started on this path of research in the first place. We were actually interested in reconfigurable electronics. The idea being that at the nanometer scale, we expected, and we have certainly observed, that it is very difficult to make a large number of nanoscale devices absolutely perfect. A significant number of those devices turn out not to work very well, or not to work at all. And so one of the issues that we tried to come up with is a way in which we could build circuits that would enable us to have a circuit that operated perfectly even in the presence of many either damaged or non-functional parts. And so that really was how we got started in all of this. And it was only after we had launched well into this research that we came across Liang's papers. And as you'll see, there was this issue of the pinched hysteresis loop that caused us to scratch our heads and wonder what was going on. And then finally we came up with the realization that what we had was essentially a semiconductor memristor. And so I will talk a little bit about the theory of semiconductor memristance. All right, so the beginning of all of this was 1997, actually, when we came up with this sort of generalization of a circuit model where we thought about the simplest possible reduction of a field programmable gate array. In other words, we wanted to think about a system that we could build that could be utilized for computation, but it had to be trivial to assemble because we wanted to make it at the nanometer scale. So the mental construct that we came up with is this crossbar structure where we have several eventually nanoscale wires running east and west, crossed by another set of nanowires running north and south, and sitting between each pair of nanowires a switch, with the idea being that we should be able to address each switch individually by placing a voltage across a pair of wires and be able to toggle that switch either open or closed. And we had a lot of ideas about that time as to what type of computation one could do with this or use it as memory. But this was really the thing that got us started. Having come up with this construct here, going from the top down, we said, okay, well, great. This is a nice circuit, but what are the devices? what is the switch that we can actually put inside of these junctions? And so I had been working in the area of scanning tunneling microscopy, and what I realized was that the process of tunneling is actually can be used as a switching mechanism. Because in tunneling microscopy, we have a rule of thumb, and that is if you're scanning a tip over a surface, if you change the height of a tip over a surface by 1 angstrom, or 1/10 of 1 nanometer, the current that flows between the tip and the substrate changes by 1 order of magnitude. So the idea was that if we could construct some mechanical or chemomechanical structure where we could vary the gap, or at least the effective gap between 2 electrodes by just a few tenths of a nanometer, we could have a switch that would switch on and off by several orders of magnitude. That was more than enough to do the types of things that we were interested in. And so that's really where tunneling comes in, because that's exactly the property that tunneling has. So we wanted to be able to build something where we could either change the physical spacing between 2 electrodes, or perhaps the height of an electronic barrier between 2 electrodes. So this was the cartoon picture that we came up with in essentially 10 years ago. We've got 2 crossed wires here of some sort, and inside we decided that what we needed to do is put in some sort of a molecule. And this molecule would have interesting properties in it. It would essentially do a bench press, if you will. By electro-reducing the molecule, we might be able to get the molecule to change its configuration, the way the atoms are arranged in the molecule, and cause the 2 electrodes to come together. But by reoxidizing the molecule, we could essentially get it to go back to its original state and thereby have an on and off switch. So this was the idea, and in fact we came up with several interesting possible molecules that we could use. And we started studying them. These were the types of molecules here. They're very, very complex organic compounds that were specially synthesized to be switches. And we were, merrily making switches that we were calling them molecular switches. And here you see the current voltage characteristics that we were collecting. And this is a 2004 publication. But again, what you see is the pinched hysteresis loop. You see this type of form here. But then the embarrassing thing is that we took this very specialized molecule, which is supposed to be a switch, and replaced it in a junction with soap, which of course was intended to be a control experiment, because soap shouldn't have anything in it that would allow it to switch. And in fact, we got very, very similar types of switching characteristics as these very specialized molecules in our system. And so this was a real problem for us. What was going on? Now, it turns out that what we finally had to do was get clever and figure out how we could get inside of our molecular devices, break them apart, and analyze them. This actually took years of effort to do because of the size of the devices and a lot of other technical issues. Eventually, what we did is we built a little mousetrap, and this was the stack that was in our devices that we were building. We started off with a platinum electrode. We actually made a very thin platinum dioxide layer because we found that what it did was it allowed the molecules that we were making to stick much better to the platinum surface. We then evaporated a thin film of titanium metal and put a thin film of platinum on top of that. So this was our molecular switch stack. And we found that when we put something like this into essentially a mousetrap and pulled on both sides, of course the weakest part of the whole thing is the molecules. And so the device would come apart at the molecules, and we could then go in and do chemical analysis on this surface here and on this surface here individually and see what was going on. And when we did, we were in for a really major shock, because we essentially used photoelectron spectroscopy to go in and look at the two interfaces. And the bottom interface, instead of having a layer of platinum dioxide on top of it, it was just pure platinum. There was no oxygen at all on this bottom electrode. The top, sorry about that. The top electrode, instead of being sorry, I'm got to turn off my phone. Should have done that beforehand. The top electrode, instead of being titanium metal, was titanium dioxide. And actually, it was an interesting bilayer of titanium dioxide, which was stoichiometric, or in other words, exactly 2-to-1 oxygen to titanium ratio. And then a layer above that, which was oxygen deficient. It had missing oxygen in the system. And so here's what we had built. Here's what we thought we had built. And here's what we actually had. And so this was actually both a huge shock and a revelation. I mean, the idea that somehow when we put the titanium down on top of this molecular film, it was sucking all the oxygen out of the platinum dioxide and actually not affecting the molecular film at all was absolutely fascinating. But this was the actual structure that we came up with. But this was good because, of course, we had been thinking that this is what we had for years and we couldn't ever explain the switching. At least when we had this structure here, and I realized that there was titanium dioxide in the system, I knew that there had been a lot of work in switching with titanium dioxide, so I decided that I needed to understand the titanium dioxide material a lot better. And just as Liang has said, there is a long, long history of these metal oxides as switches in materials. We've found about 200 publications at least in which people have demonstrated these types of current voltage characteristics. And again, every single one of them is a pinched hysteresis loop. And so there's, obviously something about this. I mean, we actually didn't have the benefit of Chancellor Kang's PhD thesis. We didn't know that there was a theorem that said if you had a pinched hysteresis loop, it had to be a memristive device. But our big challenge was figuring out if indeed these types of IV characteristics were memristive systems or memristors. And so this was the issue here. What we understood finally was that instead of having molecules in our devices doing switching, it was actually titanium dioxide. And the model is actually a model that other people have talked about and skirted around in a little bit. But qualitatively, the model is just this. You have a very thin semiconductor film. This film can be anywhere from 3 to 30 nanometers thick, depending upon who makes it. And we make them at all various thicknesses. In order to make a nice switching device, it helps tremendously if this film is actually a bilayer, where half of the titanium dioxide film is stoichiometric. In other words, this is a good wide bandgap semiconductor with a 3.2 EV bandgap. But when you have oxygen vacancies, that's a highly conductive material. It turns out that a small fraction of oxygen vacancies in titanium dioxide makes it almost metallic. But the oxygen vacancies themselves are positively charged. And so if we put a positive bias voltage on one of these electrodes, we can drive the vacancies like this and in effect make this thickness of the stoichiometric material thinner and change the resistance of the device. So in fact, if you think about it, this looks very, very similar to Professor Chua's model of the mechanical memristor that he showed earlier on with essentially the dashpot. Now, at the same time, Greg Snyder in our group had found Liang's papers and had pointed out this issue of the pinched hysteresis loop, but we simply couldn't figure out what charge and flux had to do with either molecules in devices or with titanium dioxide. So you've sort of seen this before. I mean, how it took so long to get from the resistor, the capacitor, and the inductor to the memristor. But the key, of course, for us, and it should have been for many other people, was this issue of the pinched hysteresis loop and how it related to motion of either some molecular component or, in our case, oxygen vacancies in a material. And so you've seen this equation before. This is essentially a bit generalized equation for a memristor, which just says that the voltage is equal to some resistance times the current. But the resistance is a function of a state variable for the system. That state variable could be the charge, but it could be something else as well. And so this is what we looked at. What I did was I actually put together a very trivial electrical engineering model, essentially an equivalent circuit for this titanium dioxide device. And so I essentially conceptually thought of having two resistors, one resistor which has a total resistance that is determined by the oxygen vacancy material, and the other by the pure material like this. And I considered both of those resistors essentially to be variable resistors with a connection between the two of them, such that if I slid my slide wire here, I'm essentially changing both resistances simultaneously. And so I can write down a very simple equation based upon this circuit here that relates the voltage of the device to the current through the device here, like this. Now the question was, what about the oxygen vacancies? Well, the oxygen vacancies will actually move in the device, at least conceptually, because there is, they have a mobility associated with them. So if we apply an electric field across the device, that's going to cause the vacancies to move back and forth across the device, like this. And so you can write down a very simple equation here where W is the state variable for the device. Okay, and the state variable, we're just going to say that that's the width of the substoichiometric material. This is the mobility for the vacancies in the device, and then this is just essentially the field that those vacancies are seeing. And so if you look at these two equations, they are exactly the equations for memristance. It's trivial to solve them and actually show that the memristance for this device has this form here. And as Liang showed, the most important thing about this equation is that it has an inverse square law with respect to the thickness of this layer. Now what that means is that memristance is 1,000,000 times more important at the nanometer scale than at the micron scale. And it's effectively unobservable at the millimeter scale. So one of the reasons why memristance really hasn't been very important for a long time is that devices haven't been at the nanometer scale until just recently. Now that we're getting to the nanometer scale, people are seeing memristance all over the place. I mean, we've seen that, right? So there's hundreds of papers out there where people are now seeing memristance, but it's because of the fact that memristance really is the result of two coupled equations of motion, one for the dopants, if you will, or charged vacancies in the case of titanium dioxide, and one for the electronic transport. In this case, we've used linear versions of both, so these are both versions of Ohm's law. But this is really the issue. Memristance is a fundamental property of circuits, but it's a property that is emerging and becoming more important and now even dominant as we're getting to the nanometer scale. And so now is the time that we really have to understand it to either avoid it, if that's what we want to do, or utilize it. And so I'm running out of time here, but the issue is that Dima Strukov in our group was able to just take these very simple equations here and model memristor. And so you can see that those two simple equations for the electron transport and the mobility or the movement of dopants in a material does give a pinched hysteresis loop like this. And when we go to higher and higher frequencies, or we do the higher and higher frequencies is shown here, so you actually get a line. Or if you actually do this in steps, you can get multiple loops that look like this. You also saw some very interesting pinched hysteresis loops in the data that Liang showed, and we noticed that as well. This very simple model that we put together can actually reproduce practically every IV curve that we've seen in the literature in terms of things that look like this. There's a lot of people who've been talking about negative differential resistance. There's tons of papers about negative differential resistance, anomalous resistance, this or that. It's all memristance. It's memristance that wasn't understood. So when all of these papers on NDR effects, it's just a memristance effect, or you can see IV curves like this. And then here is in our paper, in our Nature paper, this is the only experimental curve that we showed in our paper there. This was just a simple device that we built that we showed that the theory could model very well. So the bottom line message here is that you can make a semiconductor memristor, and that the memristance is the result of coupled ion-electron motion in the system. Dmitry Strukov is here, and there's going to be a poster that you can see at lunch and later on this afternoon, where we go into much more detail of the theory of the semiconductor memristor. Experimentally, we've actually built these things by the thousands now, maybe tens or even hundreds of thousands. This is a picture of a bunch of memristors in a row. There's a bottom nanowire here, 50 nanometers wide. This is platinum. We have a thin titanium dioxide layer and a bunch of layers over. That's the general picture there. And so here is the IV curve that we're getting. You see that this is actually a somewhat more complex IV curve. Now we're working with systems. Now that we understand that we've got semiconductors involved, we're actually intentionally making good metal semiconductor connections, which are Schottky barriers, so that we can get nonlinearity. So we're intentionally expressing nonlinearity in the electron conduction through the system, as well as we observe significant nonlinearity in the transport of the ions as well. So these things are at low voltages, they can be memristors, but in fact, generally they're memristive systems because of the extreme nonlinearities of both the transport and the electrons. So the conclusions for this talk are that the switching mechanism for devices is field-induced drift of positively charged oxygen vacancies. I haven't shown you proof of that in this talk. We have proven that, and there's a poster out here where you can take a look at that. This is the first experimental realization and physical model for a memristor. The memristance arises in these semiconductor systems naturally when you have the coupled transport of the dopants and the charge carriers in the system. And finally, we believe that memristor-based memory and storage could replace flash, DRAM, and hard disks in the not too distant future. So this is highly technologically relevant as well. And so at this stage, I think I'd like to see if there's any questions about what I've said so far. Yes?
When you make the film pictures very small,
There's a,
are you getting a large capacitance that's going to limit your speed?
Yes. So the question was, in these circuits that we're building, if you sort of look at things like this, yes, there's a very, very large, in these measurements here, there is a very large stray capacitance in these measurements, and that actually limits the switching speed that we see in these devices. And so we actually are able to see some speeds as fast as 10 nanoseconds, but that's limited by the stray capacitance in the systems. However, there's also another poster out there. You're actually going to see that we've actually built a hybrid memristor transistor integrated circuit where now we're able to shorten up the sizes or the lengths of these nanowires significantly, eliminate a lot of that stray capacitance. So in an actual hybrid integrated circuit, you don't have really long nanowires going off to huge contact pads. You actually have these devices, really very small. And at that point in time, the capacitances of these things are much smaller than the native capacitance of a transistor, for instance. So there's not really an issue in a true integrated circuit. Yes, there's a question back here.
Can you inverse your structure, your layered structure, by an electric field?
Yes.
You can have the substrate hermetic dioxide.
Yes, and there's actually a poster outside that shows that. We've done that. So that's one of the proof points that this theory is right. That you can actually invert the sense of the switching. Yes.
Have you looked at the thermal properties as it changes temperature?
So the question is, have we looked at the thermal properties Not in a great deal of detail yet. I mean, we've done simple things like taken a memristor and baked it on a hot plate for 250 degrees, and then thrown it back on a curve tracer and seen that there wasn't very much in the way of changes. We've done some other experiments where we've seen that the internal temperature of memristors, depending upon how they're built, actually can get quite high. Sometimes the internal temperatures of these things can get up to maybe 500 degrees C, but that's not it's not necessary, but it does happen depending upon the structure. Yes, question here.
Yeah, actually, I guess I'm having an issue with trying to understand whether this is just all semantics. Ultimately, most universal memory technologies that are out there right now, MRAM, chalcogenide, and such, all operate through this particular mechanism, which is a memristor. I mean, ultimately.
No, I totally disagree.
Okay,
So all of those other memory technologies are capacitive. You're charging a capacitor, and the capacitor essentially drains through a system. I mean, here you're actually moving the dopants in a bulk semiconductor.
No, actually, MRAM, a spin, any kind of MRAM is actually polarizing.
Well, that's so MRAM is a different case. I mean, we should take this offline because this is not a trivial. This is not a. I mean, this is something that takes a lot of explanation to get through. Okay. You've already had one, so one more. Yes.
I'm curious about the distribution of dopants. You draw it as a straight front of diffusion or ability, but I would think there's a fingering instability. If some dopants get ahead of the rest, that's a high field region, and you have some sort of tailored stability.
Well, this model. Well, I mean, you're absolutely right. What you have to realize is this model that I presented here is essentially at the freshman level. Okay, and so we've gone much further than that. And again, there's a poster outside where you can take a look, and we've gone much further than this very simple model. But the simple model is just to demonstrate that there is at least a plausibility argument for why this is memristance. But we've done a full-blown numerical simulation outside.
It's time to move on to
Yeah.
the second part.
Okay. All right. Thank you. So I apologize for Phil. He got sick yesterday, and he really wanted to come here and be at this. But since he was scheduled to speak right after me, I just said, okay, I'll give your talk. So this is a talk starting to look at some applications of memristors in different areas. And this one is going to be an application to logic. Essentially a different type of digital logic than you may have heard of before. So digital logic was invented by a graduate student named Claude Shannon. He's a very good graduate student, but at the age of 20, he went to MIT and went to work for Vannevar Bush. And Vannevar Bush put him to work on this great big huge mechanical analog computer that he was building. And it took Claude Shannon about 3 weeks to get really sick of that. And he essentially sat down and scribbled off a couple of pages and in the process invented digital electronics. And so what did Claude Shannon do? Well, what he did was he realized, because he'd taken a class in philosophy as an undergraduate student at Michigan, where he learned about Boolean logic, was that the Boolean logic functions and, or, and not could be implemented by series and parallel switches and by relays. And so, he wrote an 11-page, essentially master's thesis, which was the creation of digital logic. And practically everything that we do today in the realm of digital logic comes out of this work that Claude Shannon did. And so that's really very interesting. And so we'll see, if we can sort of push on this a little bit in different ways. Now, before we knew that we had memristors and we were just playing with actually fairly crummy molecular devices, Phil Kikas actually invented what he called a crossbar latch. Okay? The idea being that how could we actually take a signal in and latch it and store a logic value in a memory. And the idea that he came up with was really very beautiful and very elegant. The idea being that if we have two of these switches, which we now know are memristors, and we arrange those two switches such that their switching polarity is opposite like this. So one has a switching polarity pointing down, one has a switching polarity pointing up. Effectively, if you apply an appropriate voltage to these devices, you will guarantee that one is forced to be closed and the other open. And if you have the other polarity on the device, that will force this one closed and the other one open like that. And so if you essentially take an input signal into a little device like this, and you've got two clock lines, what you can do is, depending upon the polarity of the input data, you will either force this switch to be open, that one closed, or the opposite sense, and thereby afterwards, in a subsequent clock pulse, you can open up a switch here, and then by driving signals through these clock lines, you can get a data out signal, which is the latched value of the input. Or if you do it properly, if you essentially reverse the signs on C1 and C2, you can get an inverted output of that signal. And so I'm not going to dwell on this too much, but it was a pretty clever idea for being able to both get signal restoration and inversion in a nanoscale circuit without any transistors. So that was really the concept here. And we did it. We built this thing. We showed that it worked. It wasn't fantastic, but it was a new type of idea. And in fact, Phil Kikas, since he's not giving the talk, I can say this. Phil Kikas won Researcher of the Year from Small Times Magazine for this idea in 2005. But here the whole issue is that if we had, at that point in time, voltages in the range of, say, 0.3 to 0.4 volts, we could successfully latch that signal and output the inverse signal. Or if we were below threshold, essentially we got a failure to latch. And this sort of three-state output was actually viewed as being very interesting. But again, the whole issue here was this was a demonstration of signal restoration and inversion with no transistor, no three-terminal device, with a couple of memristors essentially, but with not the greatest operating margin. Now, having done that, and especially after we started to understand what memristors were, Greg Snyder came along and said, aha, I can do better than that. I can actually figure out how to make a latch with only one memristor. I mean, after all, a memristor is a stateful device, and so it in and of itself is a latch. And so then with Greg and some other people, we essentially thought about doing another type of conditional operation, which at that point in time we were calling conditional copy with inversion. The idea here is if we have two latches which share a common line like this, and we call one this a driving latch and a receiving latch, or a driving memristor and a receiving memristor, we can do an operation which forces this particular memristor open, and then we can do what we call a conditional close. In other words, if we put a bias voltage here and here, if this memristor is closed, the potential between here and here is very small, so nothing happens to this guy. Whereas if this one is closed here, then, so if this one is, I'm getting ahead of myself. I'm trying to go too fast. So if this one is closed, there's no voltage that goes across here, so this switch is unaffected. Whereas if we start off with a switch which is open here, that will force this switch to be closed. So that actually shows you that what we can do is we can take the state of this switch, which is a resistance, either open or closed, and we can copy the opposite of that state into this switch here. Okay? And if you state that in English words, what we've done is the operation if y equals 1, then z equals 0. Now, at the time, we actually were able to figure out that this very simple statement is actually computationally complete. And we got very excited and kind of dizzy at the time and thought, wow, we've discovered some completely new type of logic that was unknown before. Well, maybe that was a little bit over-enthusiastic. When in doubt, read the literature. And so we came here to Bertrand Russell. So it turns out that Bertrand Russell had figured this out. Actually, I mean, even before that, of course, Boole had figured this out too, but Bertrand Russell had worked on this in 1907, and he called that operation material implication. And so material implication for Bertrand Russell was very important because it was the basis for him of all of logic. He essentially based everything that he did on material implication instead of and, or not. Okay, so because it turns out that material implication, along with either a simple false statement, false operation, is a complete basis for universal computing. Now what that means is that we can actually use memristors to do digital logic, but digital logic using implication instead of NAND. And so here is the world's smallest micro or nano processor in this case. These are 30 nanometer nanowires in this case with memristors in between. And what we did here was demonstrate the function of a experimentally, we demonstrated the function that I just showed to you of the implication. The way you read this is that Q is replaced by P implies Q. And so we look at Q as the output, P and Q as the input. This shows the data for such a thing, essentially initializing P and Q and then performing the conditional operation, which is essentially pulsing both of these two simultaneously and then reading the output. And what you see is we do indeed see the truth table for the implication statement. The great thing about this is instead of having just simply like a 100 millivolt differentiation or margin between my on and off state, here we actually have 3 orders of magnitude. So there's a 3 order of magnitude difference between what's the on and off state in terms of either the current that we measure or the resistance of the device. So this is really a very a spectacular result, I think. And I can just show this to you and state, well, okay, Bertrand Russell proved in 1907 that this is effectively computationally complete, and you might not believe me, but what we have done is we've sort of gone one step further, and we've shown that you can make a NAND with 2 implication statements. And so here, this takes 3 memristors like this, call them S, Q, and P, and so we have a first step, which is just S is equal to false. In other words, we just open this. Then after this, we can do a step which is S is replaced by P implies S. And then we can do S is replaced by Q implies S. And if you look at the truth tables, that's the same as P NAND Q. All right? And then this electrically shows exactly that we did all of this. And so we essentially initialize Q and P in the various states 0, 0, 0, 1, 1, 0, 1, 1. And you can see that we've, at the end, we did achieve the NAND output logic state for the system. So this is really a very different way of looking at logic. If you sort of try to compare, you know, and it's not a fair comparison, I realize, but if you sort of compare just the area required for the NAND itself using memristors, it's a factor of about, well, quite a bit. I mean, it's 15 or so. So you get a very significant difference in just the area required if you're going to be doing NAND with transistors and a simple NAND gate using memristors. Of course, there's a cheat here because these are passive devices, and so you need to drive these devices here. But if another way of looking at it is if I wanted to take just a couple of memristors and I wanted to mimic the behavior of just 2 memristors with a digital circuit, what would it take? Well, this is what it would take here. So just to do 2 memristors would take 24 transistors in the form of gates here that you see. But of course, you have the driving circuitry which would exist for this. So one type of idea that we've looked at for actually doing logic is a system that might look like this, where you've got a linear array of memristors, which would be the computational part of the system, plus 2 demultiplexers that would enable us to energize, two of the memristors simultaneously, because that's what you need to do in order to do some type of logic operation. And then the controller and driving circuitry and all of this. This looks rather complex, but in fact, this type of system here could very well be very much smaller than the equivalent circuitry that you would need for a digital system with all transistors. And again, the reason is because the memristors themselves are not only logic gates, but they're latches at the same time. So they have state. So you do a logic operation, and the output of that logic operation is stored in the gate itself. So you don't have to have this issue of going back and forth between operators or gates and latches. So that's a key advantage. Also, if you have a type of computation in which you want to do local computation in a sea of storage somehow, think of having a very large cross-point array, cross-point memory made of memristors. Well, you could dynamically define a row of memristors anywhere within that two-dimensional array of logic to be a processor and do local processing on that. And then when you're done, you can just sort of release all those resources and then go someplace else in the system. So that's really the power here, because memristors in this particular sense can be registers, memory, or they can be logic gates. And you can choose at any point in time which it is that you want them to be and go back and forth between them. So I'm going to summarize this part of this particular presentation by saying that if you have memristors, you've already got a state machine, which is a pretty interesting issue. A linear array plus a demux is trivial in terms of geometry and can be extraordinarily dense. The state is encoded with the resistance or impedance or memristance or whatever you want to call it, not the voltage. So that's a very different paradigm for how you think about circuitry. And because the state is a resistance, there's no static power dissipation in this circuitry. The only time you need power is at the instant you're either performing an operation, and then you're essentially pulsing two memristors simultaneously, or you're reading the result out, which can be done at a very low resistance and very low power. So there's practically everything else in the circuit is off, except the exact part of the area where you're looking at. These devices are non-volatile. I mean, I haven't really said it so far, but we've had devices in our lab for years that we've set at a particular state, and they haven't changed a bit in several years. And in fact, we've done some measurements of activation energies, and those measurements, whether you believe it or not, the measurements say that the states should be stable for 100 million years. So, I think that this is a pretty good long-term memory. I mean, I'll accept several orders of magnitude off of that as a memory. Material implication and the false statement, those two together are computationally complete, and false is trivial. It's not like a not operation. So you can do complete universal computation with no three-terminal devices as part of your gates. Okay. Again, you do need transistors out there somewhere driving it. But the whole issue here is that it's stateful logic. The same devices are logic gates and latches together. And it's my belief that memristors effectively become power boosters, if you will, for transistor integrated circuits. I mean, Liang showed, and we sort of showed here, that in order to mimic the characteristics of a single memristor or a couple of memristors requires a lot of transistors. And so if you turn that around, you can think about going back and looking at your integrated circuits and saying, well, here's a bunch of transistors, and really all they're doing is something that looks like a memristor. You can rip those out, all those active devices, replace it with one passive device, and thereby obtain a shrinkage of your circuit and a significant decrease in the amount of power that's required to operate it. And so we're essentially thinking that memristors could essentially introduce a new type of Moore's law where you're able to get more and more transistors onto a circuit because, in fact, what you're doing is you need fewer transistors per function by going into hybrid circuits and using memristors as either latching elements or even on-demand logic elements in a system. So again, I come back to the point that I made at the beginning of the first talk that I gave, and that is we really need to ask how the nanoscale world wants to compute and not impose our preconceptions. I mean, it turns out that for NAND logic, transistors are the ideal basis for that type of logic, but there's other types of logic that are computationally complete. Implication is an example of one of those, and the memristor is the ideal basis for implication logic. So thank you very much for your attention. On behalf of Phil.
So maybe if you have a question, we can entertain a few questions. You can ask. Yeah. Okay.
Do you foresee a wear-out phenomena such as flash has?
Yes. These devices are limited in their endurance. Various people are looking at that. I think the highest published endurance that I'm aware of with these devices is 10 to the 7 cycles. That's not great for a general logic system. However, I don't think that that's a fundamental issue. I think that it's very, very early in the engineering of these systems. And if you actually think back to the original transistors didn't switch that often in the old days, or didn't last that long. So we're still in such early times that I don't think its endurance is I mean, it is a big issue now, but I think it's one that's going to be engineered.
What are the limitations on being able to sell this to people, side by side and long term?
Okay, well, we think that eventually we can build these things down to at least 4 nanometer half pitch, and maybe even smaller than that. And there's reasons for that, and it's because, well, I mean, it would take a while to get into it, but it was a part of a comment that people talked about. You get fingering. I mean, the actual size of the switching element is actually very small. It's nanometer scale. It's smaller than the actual junction. So we think these things can get down to 4 nanometers on a side, but more than that, this is a trivial technology to stack. There's no single crystal that's involved here, and so you can stack these things one on top of the other with interleaving layers of some separation material very easily. So that for a memory, the total density that you can achieve, it's easily conceivable that you could get many terabits per square centimeter using this type of technology.
Yes, one last question, please. Yes.
Yeah, one more question. In your last slide, you mentioned that you have extremely good data retention. Can you give me a number for the activation energy?
1.5 eV. But it's 1.5 EV not for an electron, but for an ion. So the frequency factor is very much smaller as well. So that leads to very, very long times.
Okay, thank you. Thank you, Stan, and one to Phil and one to you.
Okay, thank you.
Thank you. So now we are finishing a little bit earlier than scheduled, but we will take a break until 11:15. Please take a look at posters outside and enjoy, and let's get back at 11:15. Thank you. Thank you very much.